Okay, so I want to talk to you today about involvement in space missions of South Africa, and mainly the missions that I'm also currently involved in and had been involved in the past, like the Rosetta mission when I was working at SSTL in the UK. Okay, so let's get started. So the content of today will start off with the ESA, European Space Agency Rosetta mission, and then I will say something about the DeOrbitSail project. It's a European Union project, FP7 projects, and they also involve universities in other countries outside Europe in these type of missions, and we're fortunate that we involved in 3 missions actually of these FP7 type projects. DeOrbitSail, remove debris, and then also QB50. Okay, let's look at the Rosetta mission, and I think before I'm going to talk about this slide, I have a short video that was downloaded from the internet. Unfortunately, the quality is not that good, but it gives you at least an overview, a quick overview of the Rosetta mission, and then we can talk about the specifics where I've been involved in. I hope the sound will work.
The European Space Agency is
Can
about
we
to launch
turn up the
first
volume
ever
some?
spacecraft designed to orbit a comet and land on its surface. After a mission postponement of 1 year, the Rosetta probe is now finally attached to an Ariane 5 rocket on the launch pad.
That was
ready for liftoff.
2004.
Scientists, engineers and journalists have gathered at the French Guiana launch site for what promises to be a historical moment in European space exploration. Named after the ancient stone used to decipher the hieroglyphs, the Rosetta space probe will perform an in-situ study of the comet Churyumov-Gerasimenko. It will carry a complete laboratory almost 700 million kilometers from the Earth, where it will unravel the mysteries frozen deep within the comet's icy core. This will be the 3rd time that ESA has visited a comet. In 1986 and 1992, the Giotto probe flew past 2 different comets at close range, providing scientists with the best ever images of these cosmic icebergs. Like Giotto, Rosetta will use the gravitational pull of planets to catapult itself across space, swinging around Earth and Mars to gain momentum. This will allow it to speed up and travel a huge distance with only a small amount of fuel. After a 10-year journey, Rosetta will pass into an orbit around the comet, less than 10 kilometers above its surface. Rosetta's instruments will be activated, and for the next 17 months they'll study the dust and gases given off by the comet as it's warmed by the sun. It's this material that gives the comet its characteristic double tail, made up of compounds frozen within the comet for billions of years. Rosetta will also drop a sophisticated 3-legged lander onto the surface of Churyumov-Gerasimenko. Using a special harpoon to attach itself, this mini laboratory will conduct a close-range study of an environment which has hardly changed since the birth of our solar system. Rosetta has been developed by a consortium of space companies, universities and research institutes from all of ESA's member states. The result is a set of 21 cutting-edge instruments that have to perform reliably after 10 years of hibernation and at extremely low temperatures. Europe's scientists are eagerly awaiting the probe's first images of the comet, which should be sent back to Earth in 2014. Rosetta will then be ready to unlock secrets of the universe that have been kept on ice for the last 4.5 billion years.
Okay, so as you've heard, 2014, that's where we're now. But the mission already started in 1993, mainly in DLR, Deutsche Luft- und Raumfahrt in Germany. And when the mission was planned, initially they decided to launch to a comet called Virtanen, and the launch should have happened in January 2003, but the satellite was not ready. The satellite is a massive 5-ton satellite, but it wasn't ready, and then they had to quickly choose another comet, so they chose the comet 67P, Churyumov-Gerasimenko, named after a Russian astronomer. And that was the new target, and it was eventually launched 1 year later in March 2004. And then the satellite on its way to the comet took about 10.5 years, and it arrived at the comet about a month ago, 6th of August. And they suddenly also, when they got closer to the comet, realized the comet shape was different to what they thought initially. It's more the shape of two big rocks connected to each other, almost like a yellow duck that you used to play with as a child in the bath, that type of shape. And then in November this year, the lander will be released, a 100-kilogram lander will be released from the satellite, and from a 10-kilometer distance it will then descend onto the comet. Okay, the project aims was to be the first spacecraft to rendezvous and land on a comet. The J2 just flew past the Halley's comet. Then also to characterize and analyze the comet nucleus, to search for organic compounds, to study the comet activities and developments over time. And the lander on the comet will happen when the comet approaches the sun. So the comet gets heat up by the sun, and more material is then released from the comet, as you've seen in the video clip. And they also think that these type of comets delivered vast amount of quantities of water and also contributed to life on Earth. So that is all that has to be discovered, to see if there's any organic compounds that can prove the theory. The next is a small clip just to show you the trajectory to get to the comet. When it arrived at the comet, it was about 5 distances away, the distance of the Earth to the Sun, AU units. The launch was 2 March 2004 from Earth. So the Earth is that part there, and here's Mars. So there's 2 gravity assist maneuvers that it closely fly by the Earth and by Mars to change the direction of the trajectory, as well as to give some acceleration to the satellite, so that everything doesn't have to be done by the propulsion system on the satellite. So it's not very clear, but this is the orbit of the comet. So at the furthest point away from the sun, I think it's about 7 astronomical units away. And then there's the comet now in 2010, flying by asteroid belt. And then it entered deep space hibernation in 2011. And then in January this year, it exit the hibernation period and navigate to get close to the comet, and eventually 6th of August it arrived at the comet. So that's where it's now, and from this point onwards it will orbit with the comet round the sun, closest point to the sun, and then the mission will end round about there 1 year later. In October 2015 is when the mission officially will end. December 2015. So what was my involvement? A very small part of the lander is a momentum wheel, as you can see there in that photograph. It's a small disc, about 30 centimeters diameter, and the aim of this disc is to give inertial stiffness to the lander. So you spin up the disc to about 10,000 RPM to give enough angular momentum, and then the lander will be released from the satellite, and the orientation of the lander will then be inertially fixed so that it can land on its 3 legs onto the comet surface. So in 2000, Surrey Satellite Technology, where I worked at that stage, was approached by Deutsche Luft- und Raumfahrt to supply this momentum wheel to the lander, and they had a wheel from a Teldex company in Germany, but that wheel didn't make the specs. The specifications was to have at least 5 Newton meter seconds angular momentum, and to do it at that angular rate using less than 4 watts. The lander doesn't have any solar panels, or it does have solar panels, but not during the descent. They will not use, only batteries. So it was also important to limit the power usage of your momentum wheel. The momentum wheel also had to survive 12 years in orbit in deep space, so where your space radiation environment is very harsh to electronics. We developed this wheel using only analog electronics, and to be able to survive at least 15 kilorats of total radiation dose over this period of time. Another thing with spinning discs is you need bearings to keep your friction very low, and you cannot just use lubricated bearings because the lubrication will evaporate in the vacuum of space. Can also not be bearings where you all have metal parts, because the metal parts will cold weld from the atomic oxygen in space, and then the bearings will not work. So we use dry lubricated bearings to prevent this cold welding, and also to survive the 10 years in deep space environment. One of the tests that we had to pass with this wheel is a very strict electromagnetic compatibility tests to make sure that when the wheel is spun up in the satellite, it will not interfere with the radio systems and all the other electronics in the satellite. And also on the lander itself, there's very sensitive instrumentation to analyze the compounds and material on the comet surface. So we had to adhere to very strict numbers there for electromagnetic compatibility. And the momentum wheel was developed and delivered to DLR in less than 12 months in 2000 when the project started, delivered in end of that year. The Rosetta mission wasn't without any problems up to now. In 2006, a leak developed in the propulsion control system to steer the satellite towards the comet. It uses 24 10-Newton thrusters for this trajectory control, and they decided to lower the pressure of the propulsion system so that not a lot of propellant will be leaked over the life of the mission. They say there's still enough propellant left to complete the mission successfully. 2 of the reaction wheels on the satellite also developed problems, and they changed the software, so the satellite currently is only running with the other 2 wheels. There was a total of 4 wheels initially. This quick clip will show you the lander as it is released from the satellite, and then as it then descends to the comet and do its science onto the on the comet surface. So at some point in time, the lander is sitting there on the side of the satellite's released, ejected. The wheel has spun up, so it gives you the angular stiffness, angular momentum stiffness, so its orientation stays vertical to the comet surface, and then it will descend to the comet. And because of the small size of this rock in space, only about 3 kilometers in diameter, it does have to anchor itself to the comet, otherwise it will just bounce away from the comet and disappears into deep space. The 3 legs also have 3 drills to drill itself into the comet surface, so that it stays in one place when doing the rest of the science. Initially sends out these laser signals to map its environment, where it's located on the comet, and then it will slowly start doing the experiments to collect soil samples, analyze the samples with spectral chromatographs and other sophisticated instruments I don't know a lot about myself. And there's a total of 9 different instruments on this 100-kilogram lander vehicle. Okay, we So this is the Rosetta mission, and I'm waiting in great anticipation for November this year to see if my wheel will work. And if that doesn't work, don't tell them you know the guy that built that wheel, because then I want to be anonymous. The other projects we're working with the European Union, the one is DeOrbitSail. Also, the coordinator for this mission is at this Surrey Space Centre. That's the academic side of the company that I worked at the University of Surrey in the UK. And we're doing the attitude control system for this DeOrbitSail satellite. It's a small 3-unit CubeSat, 30 centimeters by 10 by 10 centimeters, weighing only 5 kilograms. And what will happen in this mission when it's launched in December this year, we're currently integrating the flight model in Holland at a company called ISIS, and the mission will eventually deploy a 16 square meter sail, 4 by 4 meter sail, from 600 kilometers. And normally when you don't have a sail deployed, a satellite at 600 kilometers can stay up there for 30 year plus. But with the sail, you increase the drag, the projected area of the satellite, and that means the satellite will be able to deorbit, burn out in the Earth's atmosphere within a year. And we will demonstrate that we can do that. And if this is successful, then all future satellites can be fitted with a sail that can deploy at the end of the mission life, so that the satellites can quickly deorbit, burn out in the atmosphere, and doesn't become space debris. The other mission is very closely related also to debris, space debris, and that is remove debris mission. That started last year, and the launch date will be early 2016. A 3-year project we're doing also with the Surrey Space Centre, and we're responsible for the attitude control system of 2 of the CubeSats that will be released from a microsatellite of about 100 kilograms. It will release actually 3 small satellites, CubeSats, and then one of the satellites will be captured by a net, the other one by a harpoon, and the third one will not be captured, but it will be imaged by a camera system to demonstrate that one can approach a piece of space debris, maneuver around it, and eventually capture it with some device. Okay, so why do we want to deorbit satellites? Currently, we have about 370,000 pieces, roughly estimated, that's larger than 1 centimeter orbiting Earth. And they pose a threat to other satellites. There's only about 1,000 satellites in low Earth orbit that's operational at the moment. The rest are either dead satellites, parts of rockets, and also space junk caused by collisions that already took place. The recorded collisions, first one was in 1996 when this microsatellite Ceres that was actually built by SSTL, it had an 8-meter boom, gravity gradient boom, and the boom was cut off in 1996 by an Ariane rocket stage, a French rocket stage. And at the ground station, at that stage, the engineers, the satellite was quite stable, and the next orbit, the satellite was tumbling at a huge rate, and they didn't know what was going on, that this suddenly happened. And then eventually it was determined that there was a collision, and the rocket stage cut off the boom, the gravity gradient stabilization boom. In 2007, the Chinese thought to show the Americans what they're capable of. They sent a rocket to destroy one of their satellites, and in the process created about 150,000 fragments currently orbiting Earth. So that was not a good idea. In 2009, there was another collision when a Iridium satellite, part of the Iridium constellation of communication satellites, collided with a Russian Cosmos rocket stage. And that also totally destroyed the Iridium satellite, and the Cosmos rocket stage broke up in about 1,500 fragments. So if we don't do anything about all these, and unfortunately you can't see all the little white dots around Earth there. You can see it close to Earth, but further away you can't really see it. You can clearly see here on my screen the geostationary orbit above the equator, where the satellite orbital period is precisely 23 hours solar period. Okay, so the debris distribution, currently about 2/3 of all the orbital debris in low Earth orbit, below an altitude of about 1,000 kilometers. You can see this is where the peak is at 750 kilometers of space debris. So fragments made up about 40%, operational satellites only 6% of everything orbiting Earth, and then there's rocket bodies and other objects orbiting Earth. And most of these 2/3 of all objects orbiting Earth is in low Earth orbit below 1,000 kilometers. And it can take tens and hundreds of years for these objects to eventually burn out in the Earth's atmosphere. If we don't do anything about it, the situation will get worse and worse. And this graph here shows you what will happen in low Earth orbit if we don't do anything about it. It will just exponentially increase, and in 20 years or 30 years from now, it will become impossible to launch a satellite that will last a long time orbiting Earth without colliding with something else. The geostationary orbit, you also see an increase, and in medium Earth orbit, also a slight increase over time. So what they propose we should do is that when we launch satellites now orbiting Earth, these satellites must have a post-mission disposal system on it. So at end of life, the post-mission disposal system will either boost the satellite in an orbit that's away from low Earth orbit, or boost itself towards Earth so it can burn out in the atmosphere. The blue line here shows what will happen if we do also only 90% of all satellites will do post-mission disposal, plus we will remove 5 big satellites actively by sending another satellite to rendezvous with that satellite, capture it, and then bring it down to burn out in the atmosphere. And the red one, this is the green one, is when we do the post-mission disposable on 90 satellites and remove 5 satellites. That one is just when we do post-mission disposal, and that is when we do nothing, this red line there. So there's many proposed solutions how to deorbit satellites. The one is to use propulsion system, chemical propulsion or electric propulsion system, but they are very tricky. That means at end of life, the satellite must still have enough energy and processing ability to deorbit itself. And normally when satellites reach the end of life is because the battery failed or some onboard computer stopped working, and you don't have the ability to fire a propulsion system in the right orientation, in the right way. So what we propose rather to do is to deploy with an autonomous system that's not part of the rest of the satellite. That autonomous system is monitored by the satellite, or it monitors the satellite when the satellite does no longer respond to commands from this or to telemetry requests. Then it will deploy a tether, that's a wire that will be reeled out, and then due to electromotive forces it will control the orbit so that the orbit will rapidly decay. Or drag augmentation, that's actually the easiest way to do it, is just to increase your projected area by deploying a sail or blowing up a balloon at the end of life and to deorbit this. So this is what DeOrbitSail will demonstrate, is that we can deploy a small 16 square meter sail from a CubeSat and deorbit, instead of 30 years, bring it down to within 1 year. Solar sailing history or sails in deep space. There's only 2 satellites currently in orbit that have sails deployed. The one is the JAXA, Japanese Space Agency. They built this Icarus sail system. It's a 200 square meter sail that was deployed in June 2010. It's slowly spinning, so it has wire booms to deploy the sail. And on the sail they have liquid crystal display patches to where they can change the reflectance of those patches so that they can control the attitude of the sail, so that the solar energy is used to its maximum to change the orbit. And currently this Icarus satellite is on its way to Venus into deep space. NanoSail D2 is a very small CubeSat type size satellite also that deployed a 10 square meter sail, but with no active attitude control. So passively this satellite orientate the sail towards maximum drag, where your center of mass is in front of your center of pressure point, so it will passively stabilize itself. And then this NanoSail D2, the next graph shows when the sail was deployed beginning of mid-January 2011. You can see from 640 kilometers roughly that the orbit drops very quickly down after 6 months to below 550 kilometers. And then at the end, here was when we predicted the deorbiting will take place in December that year, but due to the higher than normal expected solar activity, it deorbited much quicker, and the re-entry date was 17th of September after 240 days, the NanoSail deorbit itself. So we can do deorbiting using 2 methods. The one is aerodynamic drag, where the drag force is proportional basically to the velocity square, and you're flying roughly in low Earth orbit at between 7 and 8 kilometers per second. So and there's still molecules drifting around. It's not true vacuum, and the collisions with these molecules will create a force on the satellite for it to deorbit. It's also proportional to the atmospheric density. That's the rho term there, the projected area. So if you make that area larger and larger, you will create a proportionally larger force. And CD is just a drag coefficient or ballistic coefficient, and that varies between 2 and 4 depending on the shape of your satellite. And a sail is really flat, so for a sail that CD term is around about 2. Deorbit using solar radiation pressure. You can change the orientation of your sail, and then due to the solar particles bouncing off the sail, you can create a force onto the sail, and that can also be used to either increase the orbit or decrease the orbit of the satellite. So this is just a proposal how you can do it. So you start off in a low Earth orbit, let's say at 600 or 700 kilometers, and then you deploy the sail at altitudes above 600 kilometers. The solar radiation pressure force is larger than the drag force, so you use solar sailing to bring down one side of your orbit, make it more elliptical, so that you have here the closest point to Earth is called the perigee at below 600 kilometers, and then aerodynamic drag will take over, so that elliptical orbit will eventually become circular again at very low altitude until the satellite will burn in the atmosphere. The University of Strathclyde in Scotland already developed a concept where you deploy a large balloon, so you can package that balloon, very thin material, made of very thin material, in a small volume, and with a small canister you can then expand the balloon, and that balloon will then increase your projected area, let's say 100 fold, and the satellite will drop like a rock down to Earth within a couple of days or a couple of months. Electrodynamic tether concept is where you deploy a thin wire, copper wire normally, and then you make use of the electromotive force where you have a moving conductor in a magnetic field, the Earth's magnetic field, and by changing the direction of current flow in this wire, then you can create a force that opposes the direction of movement of the satellite, so that you bring down your orbit also much faster. The other project we're currently working on that started last year is the Remove Debris project. It's also a European Commission sponsored project, 3-year mission, and the flight will be in 2016. So we listed here as a partner in this mission because we're doing the control systems on the debris satellites. And you can see there's all other institutions, INRIA in France and ISIS in the Netherlands, small, medium enterprise business, and then the big space companies like Airbus, Defense and Space, SSTL is building the microsatellite, the mother satellite for this mission. So this slide just demonstrates the concept. So the mother satellite will release one of these CubeSats, and then as soon as the CubeSat is a certain distance away, a couple of tens of meters, it will deploy a small balloon, and then it presents a larger target. A net will be shot from the mother satellite to capture the debris, reel it in, and afterwards it can also cut the link, and then because of this larger projected area of the debris satellite, it will rapidly deorbit. The next debris satellite will be released. It will deploy 2 panels to give a bigger target to the harpoon. Harpoon will be shot, I think, from a distance of about 20 meters, and then it will reel in the debris to the larger satellite to about 2 or 3 meters, and then the link will be cut, and the debris satellite, because it now has a different ballistic coefficient to the bigger satellite, they will suddenly quickly drift apart over time. And vision-based navigation is where the 3rd debris satellite will be released, and that debris satellite will eventually deploy a drag sail similar to DeOrbitSail, just a smaller sail to deorbit. The final mission we're currently involved in is the QB50 mission. It's also an ESA science mission where 50 CubeSats will be launched into low Earth orbit, a very low orbit, 380 kilometers. The reason for that is to be below the altitude of the space station, so that it will not pose a threat to the astronauts in the space station. The 50 CubeSats will be contributed by universities all over the world. Stellenbosch University have been selected to contribute one of these CubeSats, and we're the only university in Africa that will participate in QB50. So the aim of the QB50 mission is to do in situ science down to an altitude of about 200 kilometers. At that altitude, the satellite will only last 3 or 4 days before it will finally deorbit, and it is to obtain models for re-entry research so that they can determine what is the density of the Earth's atmosphere much more accurately than the models they're currently using for deorbiting science. There's many control challenges to this mission. You have to keep the science payload, the sensor that will measure the molecular content of the upper layers of the ionosphere. Those sensors must be kept within 10 degrees of the flight direction, and the attitude knowledge of your sensor must be within 2 degrees. So this doesn't seem very tight compared to the Gaia mission that we've learned this morning, can control its attitude to 20 microradians accuracy. But you must remember, we're not sitting at the Lagrangian point where there's no gravitational influence, and we also have quite a big variation in atmospheric density. The variation is according to time, so when you fly in the sunlit part of the orbit, the density is high. When you fly in the eclipse in the shadow of the Earth, the density will be low, and the density also varies a lot with the latitude of your orbit. And the QB50 mission will be a polar orbit mission, so it will go through all the latitude numbers. as it orbits Earth. So we were asked to contribute a satellite, so we're currently developing ZA-AeroSat. This is our contribution, and you can see here in the lower right corner, this is the 2-unit CubeSat, 20 centimeters by 10 by 10. There at the top is the sign sensor, and we will deploy 4 feathers at the back, and they will act as radio antennas, UHF, VHF radio antennas, and they will also act as aerodynamic stabilizers for the satellite, like the feathers of a shuttlecock, the plumes of a shuttlecock. So at the back, these antennas will passively stabilize our satellite along the flight direction, but we will also have a complete attitude control system inside the satellite, and one of the sensors we're going to fly first time is a small star tracker called CubeStar. We developed, one of my students, master students, last year finished his masters. He developed this star tracker. It's only 5 by 3 by 7 centimeters, weighing less than 90 grams. So it's a very small camera system, and it flies a star catalog of the 500 brightest stars, because due to the sensitivity of our imager that we use here, we cannot really view stars below 4 visible magnitudes. So only stars brighter than 4 visible magnitude can be seen, and only 350 milliwatt on average. So it has a fairly wide field of view, about 50 by 35 degrees field of view, looking at only the bright stars. You will have at least 3 stars in the field of view, and that's enough to determine the attitude of the satellite. The accuracy of the star sensor on the ground, measurements show that we can determine the bore side direction of the star tracker to better than 0.01 degrees. So that is unheard of in the CubeSat community, to have this type of accuracies with the star tracker. We're also going to fly a new gravitational wave sensor. This sensor has been developed by a person that was a watchmaker his whole life. He's not an engineer, but he's very innovative. So he came up with an idea, and that can be groundbreaking if this works. So we're going to fly it on our satellite, and what he claims he can do, and I've seen it with my own eyes, is he can predict the sun coming over the horizon or the moon coming over the horizon before you can actually see the sun and the moon. Then his sensor gives huge signals out, activity due to gravitational disturbances that you get at that stage. So hopefully this can be a groundbreaking new sensor that can perhaps, if you want to go that way, predict earthquakes on Earth, when you have a constellation of small satellites flying this type of sensor. We're collaborating with Cape Peninsula University of Technology. They're supplying the radio system to us that they developed for their CubeSats. They launched the CubeSat last year, a 1-unit CubeSat, last year November. And the communication system on that CubeSat is working excellent. So we decided to fly their communication system. The rest of the components in our satellites all being developed within our labs at Stellenbosch University. We developed this attitude control system. This is 56 millimeters by 100 by 100 millimeters. And this is a full-blown attitude control system for a CubeSat. It has a GPS receiver, can determine your position in orbit to better than 10 meters accuracy. It has 2 cameras, one to measure the sun direction and the other one to measure the earth direction, the nadir and the sun sensor. It has torque rods, magnetic coils that can interact with the Earth's magnetic field, a torque coil for the 3rd axis, onboard computer that's radiation hardened, called Cube Computer, and we also supply 15 of these units to the QB50 project. So they bought from us 15 units like this. 3 units was supplied to the precursor flights that was launched in 18th June this year. So currently we have 2 units on the precursor satellites. This is the 2 precursor satellites built by ISIS in Holland, and they're currently commissioned. Just yesterday we managed to stabilize one of the satellites with our attitude control system. And the other one is, unfortunately, they have problems with their onboard computer. They're still struggling to get that to work properly. So the rest will be supplied to teams that doesn't have or lack ADCS capability, other teams from other universities. And that's my story. Thank you. And just for those that's interested, this is Sumandila-SAT that was launched from Baikonur in Kazakhstan, September 2009. And this is South Africa's first government-sponsored satellite, weighed 82 kilograms with a camera system. And this is one of the images that was taken, that we took of the Haneda airport, it's a sea airport in Tokyo, close to Tokyo in Japan. So this is the full image, 50 kilometers by 60 kilometers, and this part is only that small section that's blown up, and that part there is the small section showing 2 aircraft taxiing on the airstrip. Thank you. Just in time.
Spot on. I didn't have to be rude. Well, that was an absolutely fascinating talk. I'm sure there's some questions, and we have some time for a few questions. Anybody got a question for Professor Steyn?
Yeah, it's a push brim line scan sensor with 6 filters, 6 color bands. But unfortunately, we lost 3 of the color bands after 1 year into the mission. So that was taken with only 3 color bands. So it's really false coloring. It's not true colors.
What happened to your reaction wheels that had vibration? Was that a pre-flight problem, or did it?
That was not our reaction wheels. That's reaction wheels from Teldix that they flew on the Rosetta spacecraft. So they discovered huge vibrations, I think about after 1 year in orbit. And they don't know I think it's bearing failure. So they stopped those 2 wheels, and they're now running only on 2 wheels. They do the attitude control using only 2 wheels and the propulsion system to have full 3-axis control on the satellite. But that's the thing that normally fails on satellites, the mechanical parts. The electronics parts also fail, but that's mainly due to radiation, space radiation.
Prof, on your wheel, that's on its way to
the lander wheel.
The lander wheel, yeah. You mentioned that you're using a dry lubricant. How are you able to ensure that after 10 or 12 years that there won't be a problem with that?
We're not sure. At least we know there will not be cold welding, because the balls are made from metal, but the race of the bearing is made from Teflon.
Yeah.
So there will not be cold welding, but we still have to be able to start up the wheel. We have enough current flowing through the motor to give us about 70 millinewton meters torque. So that should overcome any static friction that's there in the beginning. But we don't know.
No ways of testing that?
They've tested it once. I didn't get any feedback, but if it didn't work, they would have say. But I'm no longer working at SSTL, so they will blame SSTL, not me.
Thank you.
Yeah, but we think it will work.
Last question.
Yes.
Can you tell us something about the drills they use in the feet of this lander? What are the complications there too?
I think they look like normal drills with electric motor. And once the lander feeds on the comet, they shot out 2 harpoons. It wasn't clear in the video clip, but there's 2 harpoons shot into the soil. Then they anchor it with the harpoons, and once the legs touch the ground, they've got touch sensors there. Then the drill starts, and it drills itself into the soil.
But it needs power, you know. You have
there's a battery, and there's solar panels on the lander as well, because the lander must live on the comet for 1 year.
Oh, it's got solar panels.
It's got solar panels, yes. But the solar panels is not used during the descent to the orbit, it's just batteries at that stage.